Hi everyone, today we're going to do some absolute value graphs and they're going to be mixed up, so there's no easy way to do these. We have to do them from first principles. Okay, in a case like this we have to say whatever is inside the absolute value is either positive or what is inside the absolute value is negative. On this side, the condition becomes x is less than 2, and on this side, the condition becomes x is greater than or equal to 2. So here, when we drop the absolute value, we get y is equal to minus x minus 2 plus 2x plus 3. When I simplify that, it is minus x plus 2 plus 2x plus 3, and so my answer becomes y is equal to x plus 5. That is a straight line graph. You're expected to recognize that, and of course for any straight line graph you've got to be able to say, well, if x is 0, what is y? If y is 0, what is x? And then the other point you need to work out here is, well, what happens if x is actually equal to 2? So if x is 2, my corresponding y value is going to be 7. On the other side over here, right, as I drop my absolute value, I have to put a minus in front. So this simply becomes x minus 2 plus 2x plus 3. And when I simplify, I get the straight line that says y is equal to 3x plus 1. I'm going to go through the same process. It's another straight line graph. So when x is equal to 0, my y value is 1. When y is equal to 0, I'm going to solve that equation, 0 equals 3x plus 1, and my y value is going to be minus a third. All right, if my x value is 2, I get 6 plus 1, which is 7. I'm going to draw in a vertical line at x equals 2. Please notice that this line is not going to be an axis of symmetry anymore, but it's still useful to have there to remind yourself that it's at this value of x that your definition is going to change. So 1, 2, 3, 4, 5, 6, 7. I'm going to plot that point over there. I think what I'm going to do is make that axis 2. So 2, 4, 6, 8, 7, otherwise it's going to be difficult to see what's happening. On this case, if x is 0, 2, 4, my y-intercept would be at 5. 1, 2, 3, 4, 5, and my x-intercept would be there at minus 5. My line would look like that. Okay, sorry, my scale is not great. All right, so my line would look like that, but I'm only interested in the part where x is greater than 2. Okay, the other part, if x is less than 2, when x is 0, my corresponding y value is going to be 1. When x is minus 1/3, my y value is going to be 0. And again, I have that point over there, which is included. And so this time round, my line looks like that, labeling that point there minus 1/3. Clearly, you can see this is no longer an axis of symmetry, but it does still clearly mark the difference between where that equation applies and where that equation applies over there. The gradient of this is going to be 1. The gradient of this, okay, is going to be 3. Okay, now the next example, there's no x outside the equation, but even still, we have to do this one from first principles. It's not the absolute value of a hyperbola, although it's clearly going to have some hyperbolas within it. So again, I do the process. I say what's inside my absolute value must be positive, or what is inside my absolute value must be negative. Here I'm dealing with the condition that x is bigger than or equal to minus 2, And here I'm dealing with the condition that says x is less than minus 2. If what's inside my absolute value is positive, the graph I'm going to draw is y is equal to 3 all over x plus 2, all right, subtract 1. I should actually make it clear that that line goes all the way across. So the graph I'm going to draw here is 3 over x plus 1. On this side over here, as I drop the absolute value, I'm going to put a minus in front. So it's 3 over negative x plus 2 minus 1. So we land up with 3 over minus x minus 2 minus 1, which is 3 over minus x minus 3. I'm going to choose to take a minus sign out there and write it like this because I think it will look more familiar to you. Okay, so now we have two separate hyperbolas to draw, and the dividing point is still going to be at this vertical line when x is equal to minus 2. Now you've got to keep your wits about you when you draw this graph because there are all sorts of vertical lines that come into play. So I'm going to draw each side in a different color, hopefully just to make it a little bit clearer to you. So if I take this graph over here, it is a hyperbola. The most important thing about a hyperbola is where is your vertical asymptote when x plus 1 is equal to 0, in other words, at x equals minus 1. Where is your horizontal asymptote? All right, in this case, there is no vertical shift, so your horizontal asymptote is going to be at 0. If x is equal to 0, all right, your corresponding y value is going to be equal to 3. Obviously, y can't be 0 because y equals 0 is an asymptote. And the other point that's of any interest to us is, well, what happens at an x value of minus 2? All right, so here minus 2 plus 1 is going to be minus 1. My corresponding y value is going to be minus 3. So now I want to put that information on the graph. Okay, this is only going to work when x is greater than or equal to minus 2, which is that value over there. All right, so I'm just drawing this. Where is the asymptote for this particular graph? Well, the vertical asymptote is going to be here at x is equal to minus 1. All right, draw it in like that. My horizontal asymptote is going to be here on the x-axis, the equation y equals 0. All right, it's a positive 3 on the top, so I know that my graph would normally be in those two quadrants over there. If x is equal to 0, my y value is going to be 3. All right, and that quadrant poses no problem to us whatsoever. We can just draw our hyperbola in like that. Now on this side, I've got to be a little bit more careful. The point minus 2 minus 3 is on the graph. Okay, so that point over there would be the point minus 2 and minus 3. I know that that's going to be on the graph. This curve would be a hyperbola that does that, but subject to the condition that x has got to be bigger than or equal to minus 2, I can only draw that piece of the graph there. Now if I do the same process, but I do it for this side, okay, now it's a completely different hyperbola. This hyperbola has a vertical asymptote at x equals minus 3. It still has a horizontal asymptote at y is equal to 0. If x is equal to 0, my y value would be minus 1. And if x is equal to minus 2 plus 1, okay, minus 2 plus 3 is plus 1, and minus 3 divided by 1 minus is divided by 1 is going to give me that minus 3. So again, I'm picking up this point over here. Now, when I draw in my vertical asymptote for that blue graph, it looks like this. All right. This would have an intercept at 0 and at minus 1, okay? But this part of that hyperbola, okay, that part I can't have because it doesn't satisfy the condition. This part just carries on like that. I know that the rest of the hyperbola is going to be over here somewhere, all right, and I need to know, so I've written that in, I need to know at least one point there just to hang my graph, okay? So if I was to take something like, suppose minus 4, okay? This point over here was minus 3, so if I put in a minus 4 plus 3 is minus 1, and minus 3 divided by minus 1 is going to be 3. So the point minus 4 and 3 would be over there. So this particular part of the hyperbola would come through like that. So you can see how just by sticking in an absolute value there, we can make our graphs considerably messier. Thank you.